Yes, I thought of another way of doing that graph. So in the last three video parts, I kind of showed the meaning behind the graphs and how you can tell that certain sections of the graph should be longer than others and what that means. As I said, this is physics class, so like those lines mean something, okay? But here's another way that I thought about doing it. So I started off by writing down what we knew, and you can see that the specific heat capacities on the top left here. Okay, so we have it's very low or comparatively low when it's a solid, it's quite high when it's a liquid, and it's in between when it's a gas. We have quite a big number for the latent heat of fusion, but a very big number for the latent heat of vaporization. Okay. Also notice the freezing point and the boiling point of this material, as that's going to be important. And in our question, the mass of the object. So let's just break it down into stages, okay? So as you know, when any object is heated, we have this shape of the graph, okay? So let's call those stages 1, 2, 3, 4, 5. So let's just do stage 1 first. So break it down into parts, okay? So what is the energy required there? We have mc delta theta, and the mass is 2.76 times the specific heat capacity, 2456, of when it's a solid, and the change in temperature. Now it says to start the graph at minus 50. That's in the question, okay? So our start point is minus 50, and the melting or freezing point here is minus 10, isn't it? So we have there minus 10 minus minus 50, which gives us minus 10 minus minus 50 is going to be minus 10 plus 50, which is then 2.76 times 2456 times 40. Okay, and putting that into my calculator gives us, okay, a big number there, so let's say 271,142.4 joules. Okay, now stage 2. So this time we're melting it, okay? So we need this formula, and again our mass is 2.76 kilograms, and the latent heat of fusion, as you can see up here, is 298,000. So let's put that in, 298,000, and again my calculator gives me a much bigger number than the last stage, 480 joules. Okay, now stage 3 is the section from when we heat the liquid now all the way up to the point where it's going to boil. So we need this formula again, so 276. Let's take our latent heat from when it's a liquid, which is that number there, 5107. And the change in temperature. Now the final change in temperature, the question tells us when it boils, it's at 125. So now it's going from minus 10 all the way up to 125, okay? So our final temperature is 125 minus minus 10. So in total, that is a change of 135. My calculator tells us that that is, okay, now this time we have a very big number, okay? So nearly 2 million joules. Okay, so we can see that the stage from cold solid up to the melting point is not that big, and then it's very big to turn it from a liquid into a solid into a liquid, and then to heat that liquid up to the boiling point requires even more energy. Now, stage 4. Okay, so stage 4 is this period here where we melt the liquid. So let's use ml, but remember which L we have to use here. We have to use the latent heat of vaporization, 1785000, a very big number, 1785000. Now you can see already that this is going to be a very big number. So 2.76 times 1785000 gives me 49266,000. Okay, now finally, our fifth stage, which is to take that gas, which is already at 125 degrees, and heat it up to 150. Okay, so we have our mass again, 2.76. The specific heat capacity when it's a gas is that number there, 2904. And now the change in temperature, well, it's going to go up to 150, and it started at 125. So that's 2.76 times 2904 times 25. And my calculator gives me 200376. Now, what do we do with these numbers? Let's plot them on our graph here. Okay. Now, I should have drawn that line maybe a bit further to the side, because I want to give myself as much space as possible. Okay, now let's call that our 0. So that's 0 degrees. Now we know that this started actually down here, so that's about minus 50. And the melting point, as the question tells us, or the freezing point, it's the same thing, is minus 10. So we're looking at around there. This is just a sketch, obviously. So then we can take that, and our 50 positive will be around there. 50 positive more, 100, and let's just extend that a little bit. And my 150 will be there. Of course, all of these are in degrees C temperature. And energy now, so stage 1 was 270,000. So let's just approximate that energy up to there. Let's call it 270,000. Now, the next stage was 822. Let's actually see if I can bring up the ruler again. There we go. Okay. So let's try and be a bit more accurate with this then. Why not, eh? So let's call that 1 times 10 to the 5, 100,000. 2 times 10 to the 5, and so on. So then we have 3, 4, 5, 6, 7, 8, 9, 10. We're still going to run out of space, aren't we? Okay, I'm going to have to approximate here. So let's just call that 2. Okay, these numbers are, okay. This number here is so big, class, that I can't actually fit this whole thing on here. So let's not try that. Okay, and we're just going to approximate. So we know that stage 1 is fairly short, and it goes from minus 50 up to 10. Now, stage 2 is about 3 times the length, okay, of stage 1. So let's draw that in. So I'm just approximating. If that's stage 1 up to there, well, stage 2 should be 3 times as much. So we're looking at something like that. Then stage 3, okay, is about 8 times, or maybe 7 times more than stage 1. So we'd be looking at something like this, up to about 125. Okay, so that's stage 3. Now already we're running out of space. So stage 4 then is very, very, very long. Okay, so then just continuing on that graph. Okay, I'm not doing this very well. That's 125. Stage 4 is very long. So much energy. This is stage 4 continued. Okay. Now stage 5 is not as steep as stage 1, but it's less steep. It's more steep than stage 3, but not as steep as stage 1. So you're looking at something like that. Okay. There we go. Whew, that was a long video. I hope it made sense though.